Thinking about acids and bases usually starts with the 0 to 14 pH scale. It is the system we use to explain why lemons are sour and why soapy water feels slippery. This is the Arrhenius concept. As shown here, it defines an acid as something that releases hydrogen ions, or protons, when dissolved in water, while a base releases hydroxide ions. For over a century, this has been a reliable way to predict chemical behavior. If you are working in a beaker of pure water, the math is consistent and the results are predictable. But chemistry does not always happen in a beaker. In the vacuum of an industrial laboratory or the dry environment of another planet, this water-based definition begins to fall apart. This equation for liquid ammonia shows why. Even without a single molecule of water present, ammonia undergoes autoionization. It displays the same reactive characteristics we associate with acids, despite the lack of hydroxide or aqueous protons. If we define chemistry only by what happens in water, we lose the ability to describe the mechanics of these non-aqueous reactions. To address this, the Bronsted-Lowry concept shifted the focus away from water toward the physical action of molecules. Under this rule, an acid is a proton donor and a base is a proton acceptor. It treats chemical reactions like a proton economy. This creates what we call conjugate pairs. When an acid gives away its proton, it immediately becomes a base, capable of accepting that proton back to reverse the reaction. However, even this model has a ceiling. In a solvent like water, different strong acids often appear to have the exact same strength. This is the leveling effect, where the solvent masks the true reactive potential of the acids. To see the actual hierarchy of power, chemists use a differentiating solvent, like acetic acid. This equation shows the result. We can finally rank the strength of these acids, from perchloric down to nitric. But the proton economy still has a limit. It cannot explain reactions involving acidic molecules that contain no hydrogen atoms to trade. The Lewis concept provides a wider lens, moving focus from protons to electrons. It defines acids as electron pair acceptors and bases as donors. This equation shows ammonia and a silver ion forming a new bond, driven entirely by electron sharing. This creates a new challenge for chemists. If nearly everything can be categorized as trading electrons, how do we predict which molecules will form a stable bond and which will remain highly reactive? The hard and soft acids and bases principle, or HSAB, provides the rulebook for these interactions. It is based on polarizability. Hard species have dense, rigid electron clouds that are difficult to move. Soft species have larger clouds that are easily deformed. Hard acids prefer hard bases, and soft prefer soft. Mismatched pairs fail to bond effectively. By shifting focus from counting hydrogen atoms to measuring how electron clouds respond, chemists predict the stability of compounds across the entire periodic table. We began by looking at a simple pH strip in a beaker of water. We have ended by tracing the invisible transfer of electron pairs between complex molecules. This broader perspective is what allows chemists to navigate extreme chemical environments. This exam question on the self-ionization of liquid hydrogen chloride is a practical application of the non-aqueous principles we saw earlier. These concepts are used to design stable pharmaceuticals and to engineer the high-performance materials used in modern energy storage. The shift from the Arrhenius definition to the Lewis model reflects a change in how we categorize matter, moving from counting individual atoms to measuring the geometry of electron clouds. The principles of acids and bases serve as a grammar of exchange, dictating the fundamental rules for how the physical world is built and dismantled.